I'm David Stringer, and this is R-2000, the Better Built House. Up to now in the series, we've been looking at the building science issues that affect design and construction. Now, we get out on the construction site, and a good place to begin is with foundations. The foundations of the Better Built House are constructed and designed with careful attention to three essential principles. Here they are.
In the Better Built House, heat flows to the outside are slowed down by increasing the insulation levels, by reducing thermal bridging, and by restricting radiant heat flows. Secondly, the Better Built House incorporates an airtight barrier to reduce the energy costs and discomfort caused by cold air leaking into the building. Finally, moisture control practices are a standard feature of the Better Built House. Vapor barrier materials control the flow of internally generated moisture to the exterior. Good drainage practices and damp proofing keep outside water, rain, and snow away from the envelope.
In today's program, we're going to look at methods of controlling heat, air, and moisture flows in basements. Our resident builder, Oliver Drerup, is going to show us some different techniques used in the basements of R-2000 homes in different climatic areas. I think that crunching noise is Oliver.
Hi, David.
Well, you finally get to get dirty.
Well, we'll see how long you stay clean.
Okay, what kind of stuff have you got for us now?
Well, we've been doing a lot of theory, so it's time to see how we put some of that into practice. What we're going to be looking at specifically today is how we upgrade foundation walls, both cast-in-place concrete and cement block. You want to have a look?
I'm following.
Well, this is good enough right here.
I want to start with a really basic question.
Shoot.
What's the rationale behind basements in the first place?
Well, it's a good question. Farmers dig a hole in a field, and they expect it to fill with water and feed their stock. Builders dig a hole in the same field, and they call it a basement.
They expect it not to fill with water,
exactly.
Right? Well, what about the question, though? Why not build a house without a basement?
There are lots of places in North America where builders do build without basements. They either build slab on grade or with crawl spaces. But it is possible to build a basement and build it properly.
Well, what are the steps, then, in ensuring that you'll have a dry basement?
Well, a good application of damp proofing will restrict the flow of moisture in the soil to the inside. Also, making sure that surface water runs away from the building with good grading is pretty important. Equally important is making sure that any water which does get near the foundation wall can be quickly carried away from the house. So you require properly installed drain tile and a real free draining backfill.
So you want to keep the water, standing water, away from the foundation. What about water vapor?
Well, water vapor generated on the interior of the building is going to be kept out of the wall section as a result of a very good air and a very good vapor barrier, as we've discussed in the previous program.
Well, they sound like pretty good principles so far. You keep the water that's out here, and the water vapor that's in there. Is that all there is to the Better Built foundation?
Well, clearly the foundation is going to be very well insulated, which is something on a conventional wall one can do either on the exterior or on the interior. Let's take a look at that now.
Well, there sure is a pile of insulation on this site. How do you decide how much insulation to use?
I really can't answer that question because there's so many variables. It depends, for example, on the fuel price in your area. It depends on what the builder's operation is like, what kind of material he can buy most inexpensively, what the soil temperature is, what your degree days are.
Okay, well, how much insulation do you use?
Well, what we do is we use the R-2000 program. By running our insulation levels through a computer program, we're able to optimize whatever the best trade-off is between price and savings so that we can ensure that we're doing the very best job for our client. As a general rule of thumb, I'd say that what you're looking for is something like R20 from the top of the foundation all the way down to the footing.
Okay, that R20 is obviously going to be good for energy savings, but is there a danger of freezing the footings?
Actually, David, if the house has been constructed to code, the footings are going to be below the frost line anyway. Insulating the wall all the way down to the footings may indeed lower the level of frost penetration, but not below those footings. And in any event, the heat loss at the lower levels of the wall can really be significant. In some cases, we might even insulate below the floor slab. But from a cost standpoint, the best way to optimize the various insulation materials is to use the R-2000 program. David, what we have here is a model of the way buildings are normally constructed on cast-in-place foundations with a brick veneer. I'm going to take this apart. We have the brick sitting on the exterior of the foundation wall, with a flashing sitting up next to the header so that any wind-driven rain that gets through that brick comes to the outside. And we have the header box, represented by these two blocks, and the subfloor represented by the plywood, sitting down on top of two sill plates, which are bolted with anchor bolts down onto the concrete. Now, you'll appreciate that it's over 100 feet around this building. And that's 100 feet plus of crack here, 100 feet plus of crack there, and 100 feet plus of crack here. As well, we have the bottom plate of the wall going on top of that with another crack. Now, in the R-2000 building, what we're trying to do is we're trying to minimize the amount of leakage through that space. And we have found by testing previous buildings that this is an area where there's often a lot of infiltration. So let me show you what we do. We start by using a closed-cell foam, an ethafoam gasket, which sits down directly on top of the concrete wall.
Now, this sort of suggests that the concrete foundation's got to be level.
It surely does.
No shims.
It really helps to have a foreman who owns a transit. You then have the plates put in on top of that. But in order to start the vapor barrier, what we do is we set the first sheet of poly either above or below this gasket, and then sandwich it in on top of the plate, or with the plate.
Okay, that's one crack taken care of.
So there's one down. Now, when you put the header box back on top of that assembly, you can now bring the poly through to the outside and wrap it. Go ahead. And that pretty well takes care of all the cracks, but there's a problem here.
Let's see, the only thing that goes click in my head is this is a vapor barrier.
Right you are.
Well, the 1/3, 2/3 rule work?
Totally violated. Any water vapor that penetrates this assembly is going to condense on this and run a very serious risk of rotting out your joists. If you use Tyvek in this location, it's possible for that humidity to breathe to the exterior, for the moisture to be left out of the assembly.
And your vapor barrier goes elsewhere?
Actually, you use that as an air barrier, and you don't have a vapor barrier there at all. But it's ideal if by insinuating the poly into the wall, you can insulate on top of the exterior of the header using something like extruded foam.
So this then becomes 2/3 of your total R value?
Exactly correct. And then you have your bottom plate of the wall on top of that, and the vapor barrier goes up the inside, the stud's sitting here, and you have the opportunity to make a seal between this tab of plastic and the poly coming down the wall.
And the details of the brick siding going to remain the same?
The brick siding would then go on as normal. Usually you'd see a wrap of Tyvek on the exterior of this, or additional insulating sheathing as well.
Okay, now, does this interface at all to insulation that may be on the exterior or the interior of the foundation?
Well, generally speaking, when you see a brick wall, you're going to be looking at a foundation that's insulated on the interior. But why don't we go to a site where we've insulated a building on the outside?
Oh, okay. You see the vapor barrier comes up from behind this insulation and then continues on to where it'll eventually be on the inside of the wall.
That's right, David. That's the very stuff we've been talking about. But its actual placement depends on what kind of a wall is going on above it. It's slightly different depending on whether it's double stud or single stud construction. And in fact, the choice of material depends on where the header is going to be placed. It could either be Tyvek or it could be poly.
Okay, this is exterior foundation insulation. Is this the only stuff you can use?
No, there are several materials that can be used for that. In this particular case, we're looking at extruded polystyrene, which is excellent, doesn't absorb any water at all, and can be used below grade under any circumstances. There's another foam material which is called Type 2, expanded polystyrene, which can be used below grade where there's good drainage. And there's also a fiberglass material which we've seen called baseclad, which actually has oriented fibers and enables drainage to take place down to the perimeter drainage around the building.
Now, this is on concrete and I don't see any nails. What's holding this on, glue or something?
Well, at the bottom, it's going to be held in by soil pressure when we backfill the building. At the top, in this case, we have this little flange running along the edge of the building, or flashing, if you will. Another way to do that, if there were a wooden plate at the top, would be to actually nail through the foam and into the wooden plate.
Okay, for the part of this is going to be exposed when the fill's added. What's the finish?
Couple of materials again. One thing you can do is use a finish which has been actually specifically designed to bond to this material, to the foam itself. Gives a very, very nice finish indeed. It's possible also to use mesh, which again can be nailed into the bottom plate, and then parge that with cement, which gives you the same appearance that you'd have in a standard basement.
Okay, what are the advantages to doing this insulation outside instead of inside?
Technically speaking, it's probably preferable to do it on the outside because it totally protects the foundation wall from changes in temperature in the soil, really gives an excellent insulation. But a lot of builders prefer to go on the inside because by building a stud wall, insulating it with fiberglass, and then putting drywall on it, they automatically wind up with a finished basement. Maybe that's the next thing we ought to go look at.
Okay, let's do it. Gee, Oliver, I've been in finished basements, unfinished basements, but this is the first basement I've been in that was finished in one corner.
Well, we've mocked this up just to show the steps of procedure involved in insulating a foundation on the inside. Let's start with the foundation itself. We've got poured-in-place concrete here, which has a barrier applied to it, which is a moisture barrier from grade to the floor, but only from grade. We leave the space above open so that any humidity that might get into the wall as a result of passing through the interior vapor barrier will be able to breathe to the outside.
Now, this isn't your main damp proofing, is it?
No, there's damp proofing on the exterior of the basement as well. It's just insurance. Another place where this whole issue arises is at the bottom plate. The bottom plate could be pressure-treated timber sitting directly on the concrete floor. In this case, we've spaced it away using expanded polystyrene that's been caulked, or alternatively, you could use something like sill seal just to keep the wood from contacting the concrete directly.
I see. So this tab of poly and this tab of poly are going to be joined to the main air vapor barrier, is that right?
Correct, and they run right through the whole building. The reason this is here is because that's where the electric entrance is going to go, and we've got to place the barrier in before the electric entrance is applied.
Okay, so where that service comes through this barrier, it's caulked or gasketed, right?
Correct.
What are you going to do with all the branch circuits, all those multitude of wires?
Branch circuits in the basement will run on the interior of the vapor barrier until they get up into the wall, and then they're going to be treated in this manner. Wherever you're going to have a plug, you'll have a poly pen.
So the wall's outset here a little bit. That's for extra thickness of insulation, is it?
That's correct. You can get virtually any R value that you want, and in fact, the wall doesn't have to be made out of 2x4s. It could be made out of 2x3s. It's non-load bearing. It only has to carry the finish. What we do then is we take fiberglass and weave it behind the first stud wall in the space, and then insulate the stud wall in between each of the studs.
Well, why wouldn't you just use big fat bats?
Because if you did that, you'd get a little space behind every stud, and you'd get a convection current in there, and you'd lose your insulation value.
And over here, the wall's moving right along?
Got a vapor barrier in place. We've got our finish here. But something I want to show you is this block of foam. We've put foam in between the joists, which is another way to handle the header area, enables you to get both a vapor barrier and an air barrier and increase the insulation levels in that area.
Right, and it's like a review of the whole show, just looking up in here, complete to the seam over solid backing with the black stuff I'm never touching again.
I can understand that. Let's just look at this service entry. Wherever you're going to have pipes coming through or any other services passing through a vapor barrier, they should always pass through at 90 degrees where possible, because then you can make just a very small hole, caulk that hole, or alternatively use something like neoprene to gasket the seal.
Wow, gee, that's swell. Ooh, there's my favorite noise.
The coffee truck.
Yeah.
That's the most expensive thing on a construction site.
I guess you're going to go follow it as you always do.
Aren't you?
No, I'm just going to stay down here for a sec.
How come?
I just want to wait a little while until they get the basement stairs installed.
You could be here for a while. I'll see you. I'll get you coffee.
Well, in this program, we looked at methods of upgrading conventional foundations. In the next program, we're going to look at different options for foundations altogether. So join us on R-2000, the Better Built House. Maybe there's an elevator in here somewhere.